all about how do you jump a car with a dead battery. The battery would die because we increase the internal resistance, and we know if we have a good battery, we can connect that with jumper cables, we can start the engine and recharge up the battery. So let's think about a simplified circuit. We have a good battery, this is your friend's car. We have a dead battery, this is your car, or maybe you're the jumper and he's the jumpee. And then whatever happens, whoever car is dead, we want to drive some current through the starter motor to get the car started. Let's start with part A. If we only had the good battery, so if the dead battery wasn't there, how much current could flow through that starter motor? So part A says, what if we only had the good battery? Let's do that circuit diagram. So we have our 12-volt battery with a resistance of 1 ohm, the internal resistance. We don't have a dead battery in there. And then we have the starter motor over here with a 0.05 ohm resistance. Let's write down our voltage law for this. So we have 12 volts, and we'll say that current I flows through this. 12 volts minus the potential drop across that resistor, 0.01 ohms times I, minus the drop across this resistor, 0.05 ohms times that current I equals 0. So 12 volts minus 0.06 ohms times I means that I is 12 volts over 0.06 ohms, which gives us 200 amps. Shows us that a car battery puts out a lot of current. Okay, next we ask how much current can the dead battery by itself drive through the starter motor? So the person with the dead battery is trying to start the car. So part B, that dead battery has a 0.5 ohm resistance, so much bigger than the live battery. 8 volts left in the battery, and hooked up to our starter motor of 0.05 ohms. We'll do our loop rule for this guy, label our current I. So 8 volt power supply minus the drop over the resistor of 0.5 times I, minus the drop over the starter motor, 0.05 times I equals 0. So 8 volts minus 0.55 I equals 0. I equals 8 volts over 0.55 ohms. And that gives us a current of 14.5 amps. So the dead battery by itself can't drive through nearly as much current. Okay, the next question is, once we set it all up, we attach the good battery to the dead battery in the starter motor, then how much current goes through the starter motor? So let's get a new circuit diagram for this guy. There's our live battery, there's our dead battery, there's our starter motor. Let's get everything labeled. So we've got 0.01 ohms, 12 volts, 0.5 ohms, 8 volts, 0.05 ohms. Let's label our currents in here. Let's call this I1. Let's call the current coming through this branch I2, and the current through this branch I3. Let's do our loop rules. For loop 1, let's pick this branch, call this loop 1. For loop 1, what we have is 12 volt potential supply minus a drop across the resistor, 0.01 times I1, a drop across this battery, minus 0.5 times I2, and then this guy, let's be careful here with this battery when we write down our Kirchhoff's laws. We're driving the wrong way through the battery. We're going from a plus to a minus, so that means we have a drop right here. So as we go the wrong way through the battery, from high potential to low potential, that's actually a drop in potential of 8 volts, equals 0. So we get 12 minus 8, 4 minus 0.01 I1 minus 0.5 I2 equals 0. So that's our first loop. For our second loop, let's take this outer loop. Let's call this one loop 2. Let's write our equation for loop 2. We have the 12 volt power supply, the 0.01 times I1 drop across that resistor, and then we have the drop across this resistor, 0.05 times I3 equals 0. So there's our equation for loop 2. Let's also write down our current law. The net current into a junction equals the net current out of the junction. So our current in is I1, our current out is I2 plus I3. Now we can get somewhere with this. We can solve this equation for I2, we can solve this equation for I3, we can plug them both in here and we can find all of our currents. So from this equation, let's see, 0.5 I2 equals 4 minus 0.01 I1. So I2 is equal to 4 divided by 0.5, which is 8, minus 0.01 divided by 0.5, which is 0.02 I1. There's an expression for I2. Let's also get an expression for I3. 0.05 I3 equals 12 minus 0.01 I1. That means I3 is equal to 12 divided by 0.05, that's 240, minus 0.01 divided by 0.05, that's 0.2 times I1. Let's put both these guys in our current law. I1 equals I2, 8 minus 0.02 I1, plus I3, plus 240 minus 0.2 I1. Simplify a little bit. 8 plus 240 is 248. 0.02 plus 0.2 is 0.22. So 1.22 I1, so we bring that one to the other side, equals 248. I1 is 248 divided by 1.22. That gives us a net current put out by the good battery of 203.3 amps. So that good battery drives a lot of current through the circuit. Now we weren't asked for what that current was. We're asked for the current through the starter motor. We want I3, so let's solve for I3. 240 minus 0.2 times I1. Put in our I1 is 203.3. And the current we get through the starter motor is 199.3 amps. So in part A, we saw that the battery by itself could drive through 200. When we hook it up to the dead battery in the starter motor, we still get almost that entire current, so it does a good job. Now the last question was, how much current passes through the dead battery? So it's asking what is I2 and in what direction. So it wants to know I2, both magnitude and direction. For that, we'll just solve the equation we found up here from our loop 1 rule. I2 equals 8 minus 0.02 I1. Put in our I1, that's 203.3 amps, and we get current I2 equals 3.93 amps. We get a positive value here for our current, which means we pick the right direction for our current. So it goes from the positive terminal of the battery to the negative terminal.